very well. So yeah, you have all the time that we planned for, so don't feel like
Okay.
you're restricted.
Yep.
You're safe, no pun intended. So Christian will be talking about safety from in-the-loop reachability for cyber physical systems. Take it away.
Do I record, by the way, or
It is
do I
already
press record?
recording.
Okay.
Yeah,
Okay, sounds good.
perfect.
All right. So, hello, everyone. My name is Christian Llanes. I'm a first-year robotics PhD student at Georgia Tech, and I'm working in the formal methods and autonomous control of transportation systems lab. And in this talk, I'll be presenting safety from in-the-loop reachability for cyber physical systems. Also, this is a joint work with my co-authors, Matthew Abate and my advisor, Dr. Samuel Coogan. So in this talk, I will discuss a method of ensuring safety of a controlled dynamical system based on a mechanism known as runtime assurance. This approach will consider a primary controller or some human operator that is designed to achieve a specific goal. These control mechanisms are not guaranteed to operate safely, so we wrap them around a safety mechanism that supervises the control action and steps in when needed. We begin with an introduction to a runtime assurance mechanism that utilizes control bearer functions, and we call it as a active set invariance filter. And I'll refer to it as ASIF in this talk. Although control bearer functions are a useful tool for specifying safety boundaries, they come with drawbacks, as you will see later in this talk, which is why we will then introduce a modified ASIF approach that utilizes a simulation of the system dynamics to address the shortcomings of directly using control bearer functions. And we call this method implicit active set invariance filter, and I will refer to it as implicit ASIF in the rest of this talk. The work in this talk addresses extending implicit ASIF for systems with bounded disturbances, and if you run a simulation of the system dynamics, we obtain a reachable set, which are a set of states your system can possibly be in at some future time. Now, computing reachable sets turns out to be generally computationally expensive, so we consider a class of nonlinear systems known
So
as mixed
your
monotone.
slides are not changing, by the way. I don't know if you have changed from number 2 or no. You're still number 2.
Yeah, it's still 2 out of 25.
Oh, okay. So then you're fine.
This is like an outline of
Yeah.
pretty much the whole talk.
Just wanted to be on the safe side.
Yep. So in this talk, I'll provide a brief review of mixed monotone systems and discuss how reachable sets are efficiently computed and how we can embed reachable set computations in the loop to maintain safety. And finally, we present an implementation of this approach in a hardware in the loop experiment for a 10-dimensional system so that reachable sets are computed in real time for the 10-dimensional system, and a quadratic optimization problem for the control bearer function formulation is solved in loop at 100 Hertz. And the point of this extended abstract is to describe how we're able to do this on embedded hardware. So now first, what is runtime assurance? So consider the control-affine system shown. Consider that you've designed a primary controller for the system, whether it be linear, nonlinear, or data-driven, such as from reinforcement learning, and you would typically obtain the state feedback estimates from the system and pass that to the primary controller. And you would obtain some possibly unsafe control input. Now, safety can be an undesirable region of the state space. And if you simply apply this control input to the system dynamics, there's no formal guarantee that the system will operate within your predefined safety definitions. Now, one technique to ensure that a system is operating safely is to monitor the control actions from the primary controller and switch to a safe controller when the system is approaching the unsafe conditions. And this switching mechanism is a standard approach to runtime assurance mechanisms, and it's sometimes referred to as a simplex architecture. However, the switching would preferably be done as smoothly as possible. For example, as you approach the unsafe region, perhaps you should slow down. Now, a useful mathematical formulation for specifying safety boundaries that has been a popular tool in controls literature is control bearer functions. Control bearer functions can also ensure that a system slows down as it approaches the unsafe region of the state space. The equation outlined in this slide considers all possible control actions that ensures an inequality is satisfied. And this inequality is known as the standard control bearer functions definition. Consider that a barrier function H such that the safe region is defined as the super level set of H. And this barrier function is 0 on the boundary and positive definite in the interior of the safe region. And we can then go back to the CBF formulation and notice that the left-hand side of the inequality is actually the rate of change of the barrier function h. And the right-hand side describes how fast you can approach that boundary. And this is encoded as a lower bound on the time rate of change of h. Notice that the alpha function is strictly increasing and maps real numbers to real numbers, and the evaluation at 0 is also 0. This is known as a class K function. Now, for runtime assurance, we want to ensure that a control action does not violate the control barrier function constraint. And to do this, we do this construction, we pose it as a convex optimization problem that ensures that a desired control action from your primary controller is safe. And this optimization problem considers the argument of the min of a 2 norm over the difference between the optimization variable u and this desired controller ud of x. Notice that if the desired controller satisfies the inequality, then it should be the optimal control action that minimizes the convex and u2 norm function shown. This is exactly what we want, so that the safety mechanism acts as a pass-through, and it only steps in when needed. This formulation is known as active set invariance filter, as I've said. And at the bottom of this slide, we show a simple example of its application to a planar multi-rotor. The multi-rotor is commanded by a primary controller based on dynamic feedback linearization, and we define a safety boundary so that the quad rotor is unsafe if it enters the green region. The top animation uses the active set invariance filter to ensure that the vehicle does not pass the boundary, and the bottom animation it simply passes that primary controller through. You notice that the vehicle, it slows down as it approaches the boundary of the safe region. And now traditional ASIF, it uses CBFs in the way shown in the previous slide. And now finding a viable set, safe set, a priori, it can be difficult to do, because this set needs to ensure that when you run a control barrier function, the control action is in your set of possible control actions, or else you may get stuck. For example, in the case of a robot that uses motors which can saturate, if your safety mechanism is not aware of the saturation and it commands an action that is infeasible, then the safety mechanism may break down. We present a method that is guaranteed to always request a control action that is viable. And in this method, we consider a smaller viability kernel that is verified safe. And control actions are non-empty on the boundary. That is, you're always guaranteed to perform a control action requested by the CBF. And this is typically done by finding a closed loop backup controller that ensures a backup subset of the safe space is forward invariant. This set may be smaller, so we would like to operate outside of it if possible, because it's too conservative. Now, to do this, we run a simulation of the backup controller at each time step to ensure that your safe backup subset is within reach of a predefined prediction horizon. This should ensure forward invariance of larger subregions of the state space by simply defining the forward invariant viability kernel. And we refer to this approach as implicit Asif, as I've mentioned before. And this is a basic overview of the important components of the algorithm for implicit Asif. Similar to this standard CBF approach, the barrier function is used, but in this case, at each time we run a simulation of the safe backup controller for a fixed prediction horizon, T. We then define a new variable psi that is the maximum over the barrier evaluations along the trajectory under the backup controller. So as in the rest of this talk, we refer to the global flow or the state transition map of the closed loop backup dynamics as phi of b. Now, similar to the standard ASIF algorithm, we use a pointwise filter posed as an optimization problem that it takes in a desired control action from a primary controller. The inequality now uses psi instead of h, but notice that the psi contains a composition of functions h and phi of b, which the derivative can be computed using the chain rule. And the first term is simply the gradient of h, and we're evaluating that at the maximizing time t star. And the second term is the flow sensitivity of the time t star, where t star is the argument that maximizes h in the definition of psi. Now, up until now, we only considered deterministic systems with no disturbance. Without appropriately considering disturbances, we get collision, as you see from this simulation. Consider the non-deterministic control affine system shown, for a bounded disturbance, and we say that a set S, or the superlevel set of a barrier function H, is robustly forward invariant if you can always find a control action that ensures forward invariance of a safe region. And in our work, we consider a system subject to a bounded disturbance. We apply a similar approach from the implicit Asif theory. The simulation of the closed loop backup dynamics with bounded disturbances requires computing the reachable set of the system to ensure that the entire reachable set does not violate the CBF-based constraint. Or in other words, consider all possible disturbances and ensure that you always have a trajectory back to the safe backup subset, so that there's not a case where a set of disturbances would lead to being unsafe, essentially. Now, the major problem with this is that computing reachable sets numerically is generally computationally expensive and difficult to implement in real time, or fast enough for highly dynamic systems that require fast control update rates. In this work, we consider a class of nonlinear systems with efficient reachable set computations known as mixed monotone systems. So we consider an approach that uses the theory of mixed monotone systems to compute reachable set approximation at a much faster rate that is possible to do in real time. Now, consider the autonomous non-deterministic system shown. As I said before, the disturbances are bounded and they're upper and lower bounded. A system is said to be mixed monotone if it can be decomposed into increasing and decreasing components via a decomposition function. And the decomposition function, it maps 2n dimensional state spaces and 2m dimensional disturbance spaces to an n-dimensional state space. There are 4 strict requirements for a function to be characterized as a decomposition function. First, if the state x and disturbance w are inputs to both state and disturbance spaces, then the vector field should be equal to the vector field of the original dynamics. And the second requirement is that the Jacobian of the decomposition function with respect to the state vector x is positive semi-definite for all off-diagonal elements. Similarly, the third requirement is that the Jacobian of the decomposition function with respect to the x hat is negative semi-definite for all indices in the Jacobian matrix. And now the final requirement is similar to the second and third, but for the disturbance vector w. Now, the decomposition function is used to construct a 2 times n dimensional embedding system for a bounded disturbance defined by a hyperrectangle, so that w is upper and lower bounded. And a southeast order on r to the 2n is defined such that 2 input vector arguments of x and x hat are said to be less than or equal to y and y hat with respect to the southeast order if x is less than or equal to y, and the reversed y hat is less than or equal to y hat is less than or equal to x hat. So a simple illustration is provided for a 2-dimensional system. Notice the vector arguments y and y hat are 2 corners defining the rectangle shown. The same is said for the x and x hat arguments. And the southeast order ensures that the y and y hat rectangle is fully contained within the x and hex hat rectangle. This partial order is defined so that trajectories in the embedding space characterize a hyperrectangle reachable set approximation generalized to the n-dimensional state space. And the embedding system is monotone with respect to the southeast order in the embedding space. In other words, if an initial set defined as the hyperrectangle is initialized for the embedding system, then trajectories that result from points within this hyperrectangle should always be contained in hyperrectangles that result from the state transition map of the embedding system. This characterization is useful because we can always bound all possible trajectories for an initial set of states, which gives us an approximation of the reachable set. Now, we assume that the closed loop backup dynamics are mixed monotone with respect to a decomposition function. Note that a mixed monotone system is mixed monotone with respect to a number of decomposition functions. And in practice, one may want the best approximation of the reachable set, which requires finding tight decomposition functions. And the figures show an approximation of 4 reachable sets given in range of initial states. Research is ongoing to find better ways to approximate the reachable set by considering transformations to obtain higher fidelity approximations. We apply this theory now to extend implicit Asif for systems with disturbances, and in our work, we're able to compute reachable set approximations at fast enough rates to ensure safety of multi-rotors. So before we dive into the algorithm, we first need to define a backup control policy that renders robustly forward invariant a safe backup subregion defined by a barrier function H. This safe set should be viable and may be conservative. One way of finding invariant sets is to consider local linearization of the nonlinear closed loop dynamics. We can find a quadratic Lyapunov function that satisfies the origin asymptotically stable for the linearized dynamics. Then we can find the largest forward invariant level set of the Lyapunov function that certifies the nonlinear dynamics. This can be done by numerically checking sort of a large number of points on the boundary of the safe subregion to ensure that the barrier function time derivative is always it's never positive within even with disturbances. Next, we must find an appropriate decomposition function that satisfies the requirements we defined in a previous slide. One may approach this by finding a decomposition function with a bounded Jacobian matrix, or finding a decomposition function that enables tighter approximations. And I'm referring you to the cited conference papers in this slide for a more detailed discussion on techniques for computing decomposition functions. And from the implicit Asif formulation, the gradient of the barrier function was a required component in the CBF inequality constraint. However, as you will see next, this means that we must take the derivative of a min-max operation, which is not differentiable. And so we use a numerically stable relaxation known as the logarithm exponential. And this approximates the minimum of a set S, where S is a finite subset of R. So define LSE of S as shown for a fixed parameter P, and P controls how tight the logarithm exponential approximation is to the real min operation. So we define a 2n dimensional vector A that describes a hyperrectangle in the n-dimensional state space with the first n and last n components of A. And so we refer to the double bracket as shown for the encased A as the corners of the hyperrectangle A. And so the corners, they scale with a base power of 2. So a two-dimensional system, it contains 4 corners. In a 3-dimensional system, 8 corners, and so on. And the logarithm exponential over the set of corners of the hyperrectangle A is defined by LSEH of A, shown here. And this function, it evaluates the barrier function over the set of corners of the hyperrectangle A, and it takes the logarithm exponential over the set of that set to approximate the minimum or the worst corner with respect to that safety condition that you defined. So now for the main algorithm, we first simulate the embedding system for a fixed prediction horizon T. We then define gamma as the logarithm exponential of H over the trajectory of the embedding system, which was as mentioned before, is a hyperrectangular over approximation of the reachable set. And we found that computing this LSE of H over all points on the trajectory is not needed. And we could reduce our computational load by considering a smaller number of points distributed based on maybe like a log-based distribution algorithm around the previous maximizing time T star. Because we know that T star, it changes continuously. And so therefore, the next iteration would have a T star close to the previous iteration. So in practice, we were able to run this algorithm with only 5 points for the log-based point distribution. And we then define psi of x as the maximum over the set of gamma, which is the size of gamma is defined by the number of points you used in your point distribution algorithm. Then T star is evaluated as the time argument that maximizes the set gamma, or in other words, we evaluate the worst corner of the reachable set approximation for a number of points in the trajectory, and we find the best case in the trajectory. So the gradient of psi, again, using the chain rule, which requires computing the sensitivity of the embedding system. And finally, the implicit Asif quadratic program is constructed to filter a primary controller, which while satisfying that CBF inequality constraint shown. Now, the main contribution in this talk is implementation of the implicit Asif algorithm in the embedded hardware for a real system with disturbances. So we consider a case study where 2 multirotators are fixed to the YZ plane. We refer to the system as the dual planar multirotator system. To test our implicit Asif implementation, we intentionally construct a primary controller that would lead to a collision. And the goal of this case study is to ensure that our implicit Asif algorithm can filter the input commands from the primary controller to avoid this collision. And the multi-rotors are considered safe if they remain within a displacement distance of 1 meters in the Y and Z axes. And so on the left-hand side are the dual planar multi-rotor dynamics, and on the right-hand side is the backup controller. And we model as a dual mass nonlinear spring and friction system. So the force commands in the Y and Z axes are from the spring and friction model, and the collective thrust and moment of each multi-rotor is commanded such that desired force vector for each multi-rotor and the thrust vector are aligned. So from the closed loop backup dynamics, we can find a robustly forward invariant backup subregion that is a viable set for the implicit Asif formulation. So in the following slide, we have results from a hardware in the loop experiment for the dual planar multi-rotors, subject to the primary controller with the intention of a collision. So this hardware in the loop experiment is run on Jetson Nano that would have similar computing power available for a multi-rotor in flight. And so we implement our algorithm in C++ on the robot operating system. And the first plot from the left is a projection of the state trajectory for the displacement coordinates. The set in green is the viable backup subset, and the set in blue is a defined safe set. And the black trajectory is the actual trajectory in the displacement coordinates. And in the red, we have the trajectory, the embedding system for prediction horizon of 5 seconds. And finally, the red set is the reachable set approximation. So notice that the reachable set is fully contained in the interior of the viable backup set. And we also ran the simulation with Asif off, and we provide a comparison of position trajectories with Asif on versus off. So in this plot here, you have sort of quad rotors that with the primary controller passing through with Asif off, and this is this safe trajectory with Asif on. So in this slide, we present more data from the experiment. The left plot is a thrust versus time plot for multi-rotors 1 and 2. And notice that within the first 0.5 seconds, the filter it acts as a feed through because the system is already within the viable backup subset. That's where we initialized. But after 0.5 seconds, the filter activates smoothly to ensure that the two multi-rotors do not collide. And on the right-hand side, we have the time within the prediction horizon, which we have 5 seconds as our prediction horizon. And this time T star, it's the time that finds the best case reachable set that is fully contained in the backup set. So the major takeaway from this is that we're simulating a deterministic embedding system to obtain 10-dimensional reachable set approximations, using the reachable sets to compute barrier functions for all worst case scenarios, and we're computing the sensitivity of the barrier function with respect to the current state. And we're solving a convex optimization problem for the CBF constraints at 100 Hertz. And this is for the dual planar multi-rotors on a Jetson Nano that acts as a small onboard computer for the two multi-rotors. So this work is a proof of concept to see whether it was possible to run this algorithm fast enough to act as a low-level filter for multi-rotors, which requires actually fast computations to stabilize the fast rotational dynamics of these multi-rotors. So in this slide, I have a software sort of design that I constructed for the algorithm. Essentially, this algorithm is run as a ROS package. As I said before, we're using sort of a Jetson Nano as this target hardware in the loop, so that this is on board the quadcopter. And the personal computer it's running each quadrotor, sort of a simulation of each quadrotor in Gazebo. And within each quadrotor, you'll have an instance of PX4, which is an open source design or stack for essentially like autonomous systems, essentially fixed wing quadrotors. And so we pass through our commands through this this ROS package called mavros, which implements this some protocol called mavlink on the robot operating system. And mavlink is used with PX4 for communication. And so you can see here, this closes the loop, and sort of these quadrators, the states are taken and were passed on to the ROS package that implements this our algorithm. Now, for some in this slide here is a video of the hardware in the loop experiment for the dual planar multirotators, sort of with physics handled by Gazebo, as I said. And you will see here that in black is with Asif on, and in red is with Asif off. So that primary controller is commanding a control action that would ensure a collision here at this point here. But with Asif on is ensuring that the quadrators are sort of both trying to get to that point where they both want to be at, being commanded by the primary controller, but obviously that would defy that safety definition we have. So it's not allowed to sort of pass too far away from this 1 meter displacement distance. So now for some concluding remarks and takeaways that I would like the audience to capture from this talk. First, control barrier functions can be coupled with a prediction of the system dynamics to increase usability. Second, in the presence of disturbances, we compute the reachable set, and we can use mixed monotone systems to generalize to a class of nonlinear system for which reachable sets are efficiently computed. And finally, the third takeaway is that implementation on embedded hardware can be achieved by combining these techniques to achieve fast in-loop reachability analysis with a formal safety guarantee for dynamic systems with disturbances. So that is it for my talk. Any questions?
Excellent. Thank you for the great talk. So we have time for questions, and then we're going to have a break. So there's a hand by Binsu. Go ahead, Binsu.
Yes, so thank you very much again for the talk. It's a nice talk. So I have a question. So I noticed that in your procedure, you also require to compute a barrier a control barrier function online. But as far as I know, so for computing the barrier function, so there's no so which means that although a barrier function exists, you may not be able to compute that. Yeah, this is a challenging point for the computing the control barrier function. So if on the fly you cannot find that barrier function, so what should be done? Or for this kind of system, you find a specific way that once the barrier function exists, you are able to compute, you are able to get that for sure. So I'm not sure which case is the case.
So you're saying that there's a point where your control barrier function, you won't find a control barrier function? Is that what your question is, or?
Yes, because there's, as far as I know, so you may not be able to find that control barrier function, although it exists. And this is one of the things you need to do online, because if we compute that offline, we don't find that, we change some condition and we do again, that's fine. But if on the fly, obviously you do not have time to do so.
So I think maybe what you're getting at is that sort of from this control, this barrier function, it's possible that sort of the solution is not in your set of possible control actions. Is that where you're implying?
I'm saying that given a set of unsafe region, you try to compute a barrier function. So although a barrier function exists, but you may not be able to find that with one configuration. So, but you want to find that on the fly.
I think he computes the barrier offline, didn't you? Am I right?
Because in the very last very few slide, he also report the time for computing the barrier function online. So I think that he computed that online.
So that's the time to evaluate the barrier function. So yeah, it's given. So we have a safe region defined by a barrier function. We are computing in some sense online a second implicit barrier function, but that's guaranteed to exist because we're computing with the backup trajectory. So we're evaluating barrier functions online, but we're not, for example, synthesizing some sort of polynomial barrier function online. Nothing like that.
Okay.
Yeah, we're not synthesizing in the loop or
it.
anything. Yeah.
Okay, got it. Thank you.
So maybe maybe Bingjo, your question would have been, what if there is no input that satisfies the last condition of barrier?
Yeah.
Within the, I mean, of course, you assume input set is unbounded, it's Rm, but in reality, it's bounded. But if in real time, there is no input that satisfies the barrier condition. So maybe that's what you were asking, Bingjo.
Actually, no, because maybe, I was thinking that he want to synthesize the barrier control barrier function on the fly. So I just want to ask whether you cannot find that, but now I make a mistake. So now I get it.
But I do like Majid's question, so maybe I will answer Majid's question because it's a good question. So one very nice thing about the way we formulated here is because we're using a backup controller to define this implicit barrier function, we're always guaranteed that at least the backup control input is available to us. So we, in some sense, we ensure that even with constraints on the input, that input is available to us. And we use a conservative invariant set that we get, for example, from linearizing the dynamics as sort of a seed to ensure that we maintain feasibility along the whole way. So that doesn't become an issue in our formulation. And in fact, it's exactly the kind of thing we are trying to solve with this formulation.
So you shift the complexity of having control input at every time to this backup controller. So that's offline you compute and you ensure that you always have a control input that can push you inside the domain of the smaller region, correct?
So that's true, but I would argue that that can even still be a pretty simple controller also. It could just be a local linear controller with a linearized backup set. If we're moving complexity anywhere, I would say it's to the online computation of reachable sets. So that's where we're pushing the computation.
Yeah, so it needs to push you always inside that smaller subregion.
Right. And that's where the computation lies. And if if you have a poor estimate, if you're not using a very good decomposition function, to use the mixed monotone systems lingo, you might end up with this kind of expanded region that's not a whole lot bigger than the region you started with, right? So in this picture, you start with this verified safe subregion. You're trying to get a larger region that you're basically checking on the fly with reachable sets. But if your reachable set computations aren't very good, if they're very conservative, then that set just won't be much bigger than what you started with. But it's always there, and you always have a safe controller available to you.
Yeah, makes sense. Thank you.
Great question. Do we have other questions? I guess, Christian, since you show also some experimental kind of effort, how sensitive are the synthesis tools that you're using to the actual platform? Do you pay attention to what the platform, clock would be, or computing delay, or processor assignment to your task or whatnot, or that is not yet being taken into consideration in the analysis and design?
Yeah, I mean, so sort of when we came up with this, we realized that this formulation was more like a low-level controller. So we were originally intended to have this sort of computed sort of on a personal computer that has, say, a lot more computational capability. Maybe send that off board to the quadrooters. But since you're doing low-level control on sort of a quadcopter, you can't really do that because even smaller delays can contribute to sort of this possibility of crashing. It's never really done in that way. Maybe outer loop controllers, possibly I've seen that done, but not in the way, not with what we have formulated sort of as this low-level controller. So we had to use the Jetson Nano capability, computational capability, essentially. So Now, time delays with this system, it's very minute. Considerably, it's much smaller if you're computing on board the quadcopter, and then sending that to sort of this. So you have like this sort of this two computers essentially. You have the flight computer, and you have this onboard computer. The flight computer does all the management of the flight software, but then you have the other computer which sort of computes all the more computationally expensive components, so that this flight computer, which may have less resources, it can focus more on commanding low-level things like drivers and motors, more as a real-time computer, if that makes sense.
Mm-hmm.
And yes, so, and this is like how we did our software design for this this hardware in the loop experiment.
Very good. Thank you. So our next session starts in a few minutes, so we have either time for more questions or other discussions.
So for the demonstration, the reason you want to use online reachability is because of disturbances. So you were using a simulated model, so you simulated disturbances then for that one?
You're referring to sort of this in the hardware in the loop experiment, right? With the disturbances. So disturbances, you don't necessarily need to, at least in this experiment, it doesn't have to be sort of explicit disturbance. It can be anything such as uncertainties in the dynamics, even the states estimates or anything like that. These all bring up their own disturbances, being inherently uncertainties. Even you can model in the way that we modeled. We didn't model the motor ramp up dynamics or anything like that. So these all bring up sort of these unmodeled dynamics, and these can account for sort of as the disturbances in your reachable set computation.
So then were there assumptions made on the bounds of those disturbances that you would want to
you have
validate those?
Yeah, we considered sort of these upper and lower bounded disturbances to be able to compute the reachable set.
I guess one question, like an interesting trade-off to evaluate would be, as you get more disturbances, the reachable set computation will have sort of more error, right? So is there this sort of nice trade-off? Is there this nice spot where you have enough disturbance where you can sort of realistically run the system, but you don't have too much error in the reachability computation?
Yeah, I mean, I even noticed that when you ramp up the disturbances more and more, sort of you're maximizing time, you're kind of not allowed to veer off too far away from the safety. That's what I was seeing from just increasing the disturbances to a certain extent, because the reachable set gets so much bigger than your viability kernel. So that's one thing to consider as well. And also, I mean, depends on how you compute your, how you find your decomposition function as well. You can have a tighter decomposition function that it computes it more sort of as an over approximation. Because sort of what we used, it's a bit more conservative than you would want. But you can always have the availability of finding a better decomposition function. And there's sort of better, I'll let him present because I'm close on time, but yeah.
So yeah, maybe you can take the discussion offline. I mean, I can send you guys to a breakout room if you want. So yeah, this is the time that the